When we go on to develop the governing elemental equations in our next lectures, you will find that many terms will need to be calculated by the integration of some function of the shape functions. Now this is not difficult, especially because we have been using syntax elements so far. So the integration is not difficult at all, but we can make it even easier if we introduce something called natural coordinates, which we are going to do now. Now these are coordinates that are local, dimensionless, and whose values range from 0 to 1. Let's see what these natural coordinates are. We'll start with the 1D element. This is the coordinate, x coordinate, and the element is line element, I, j nodes. This is the xy coordinate, and this is the xj coordinate location. And now we introduce the natural coordinates. Let's say there's a point P here, and this P can be anywhere between I and j. That's it. This means that this distance and this distance, they are variable, you can change. And this is, let's call this L1. On the opposite side of I is L1, on the opposite side of j it is L2. And the definition of natural coordinates for this system is this. There are two natural coordinates. First one, L1. This is L1 over L, and L is the length of the element, and L2 is equal to small L2 over L. Now let's consider this. If P moves to node I, then L1, I talk about the natural coordinate, capital L1 becomes 1, L2 becomes 0. If P moves to node J, then L2 becomes 1, L1 becomes 0. Does this remind you of anything? Also, let's add them together. L1 plus L2. So L1 plus L2 over L. L1 plus L2 is nothing but L. L over L is equal to 1. It means that throughout the element, from node I to node J, the sum of the two natural coordinates is always 1. You should be reminded of shape functions. Shape functions are all these properties. In fact, L1, small L1, is nothing but, according to this diagram, xj minus x over L. And x is the variable. Wherever this p is, that is x. And this x is measured from this origin on the left. So this is exactly the same expression as that for ni. Similarly, L2, small L2, is nothing but x minus xi over L. Again, the same expression as that for nj. This means that our natural coordinates for a 1D system are equivalent to the shape functions. That is, L1 is equal to ni, L2 is equal to nj for a simplex element. Now, it can be shown that function incorporating powers of L1 and L2 can be integrated very simply by this expression. L1 power alpha, L2 power beta over some length. The integration is simply alpha factorial beta factorial alpha plus beta plus 1 factorial into L. Suppose we are to integrate this expression ni square nj over length L. But the boundary system here, xi is 1 and xj is equal to, these are the locations of the two nodes. Now, first let's do it in the usual way. It is not difficult, but as you'll see, it is quite tedious. Now, ni is xj minus x over L. Xj is 5, x is a variable, and length is xj minus xi is equal to 5 minus 1 is equal to 4. There is a 4 here, and nj, the expression from is x minus xi over L, which means that x minus 1 over 4. We have to integrate it over this element. So from 1 to 5, and we have to integrate this 5 minus x over 4 square x minus 1 over 4 dx, which is 4 power 4 square 16. This comes out, and we have this expression 25 minus 10x plus x square. This one is first one, and then that x minus 1 dx, which is equal to 1 over 64 1 5. Simplifying, this is 25x minus 10x square plus x cubed minus 25 plus 10x minus x square dx, which becomes x cubed minus 11x square plus 35x minus 25, which is, let's integrate with this, 4 minus 11x cubed over 3 plus 35x square over 2 minus 25x. We'll take limit from 1 to 5, and taking the limit, we can verify that this turns out to be 1 over 3. Now compare this with the factorial formula. Ni square nj dx over length. Now this can be replaced by L1 square L2 dx over length, because shape function and natural coordinates, they are equivalent. Alpha is equal to 2 and beta is equal to 1. Now 2 factorial 1 factorial over 2 plus 1 plus 1 factorial into length, which in this case is 5 minus 1 4. Now 2 4 into 3 into 2 4, and we have 1 over 3. So we saved a lot of computational effort. Now another interesting thing about this is it would have given us the same result if it was ni and nj square, because on the right hand side we have only have alpha and beta. We are not concerned with ni and nj. Makes it very easy for us to integrate expressions containing shape functions. Now let's take up 2D element. For 2D element we have I node, J node, and K node, and in this case let's take point P here. Now this P divides this area of the element into three areas now. Calling this as area 1, this is the area opposite node I. Area opposite node J, we call it A2, and the area opposite node K, we call it A3. Now, it's obvious that we are going to have three natural coordinates for an area element. L1, A1 over A, L2 is equal to A2 over A, L3 is equal to A3 over A. Now, if this point P moves to node I, then L1 becomes 1 and L2 and L3 becomes 0. And similar is the case if it moves to node J or node K. This is a property of shape functions. Also, we know that sum of shape functions is always 1 anywhere. Let's see if that is the case with the natural coordinates as well. L1 plus L2 plus L3 equal to A1 plus A2 plus A3 over A. But A1 plus A2 plus A3 is equal to A, so A over A is equal to 1. So we have seen that natural coordinates, they also vary from 0 to 1. 0 is the minimum value, 1 is the maximum value, and this 0 and 1 happens on the three nodes, and anywhere including the nodes the sum of the three natural coordinates is 1. So we can, so we are justified in saying that L1 is equivalent to Ni, L2 is equivalent to Nj, and L3 is equivalent to Nk. Now, as was the case with 1D, we have simple integration formulas. For 2D case, as expected, there should be area integral, L1 alpha, L2 beta, L3 gamma over a certain area A. Its integration is simply alpha factorial, beta factorial, gamma factorial over alpha plus beta plus gamma plus 2 factorial into 2a. Now this is when area integral is involved. In 2D cases, there are also occasions when we have to calculate a line integral in a 2D problem. For example, let's say this is a ball with pressure like this. Now we mesh this ball with many elements like this and take this element now as a sample. So this is a 2D problem, the area element, but the loading is applied only on this one line. We have to integrate this sort of loading over this line, not on this whole element. So in such a case, we'll need to integrate it over this line. So in this case, the integration formula will be very similar to one for the 1D case, and that is L1 alpha L2 beta dh over a line h. This line length is h, and write it exactly the same as last time. because here only two shape functions are involved, not three. So only two natural coordinates are involved. We're talking about one line here. We have alpha beta over alpha plus beta plus 1 factorial. Then we have left. Now, what would be an example of area integral for a stress analysis problem? Again, take a body like this with certain small thickness t. This body has a weight with x in the vertical direction like this. This is body force. Now, when we mesh this body, we have many elements like this and so on. Now, let's, as a sample, let's take this element. This is an element with some thickness, but its thickness is constant. So, plain stress problem. So, you can take this out. What happens is we'll be required to integrate some quantity over this whole area, because weight acts on the whole volume. Now, in this case, volume is area multiplied by thickness. Thickness is a constant, so it can be taken out of integration. So, what we are left with is area integral over this whole area. So, in that case, this is the expression. As an illustration, it's obvious that it's an area integral, so we need to use the first formula. So, first of all, this quantity, actually we have to evaluate this one. Now, because Ni is equivalent to L1, write it like this, and here we don't have Nj and Nk, so all we need to do is L2 power 0 and L3 power 0 again, because something power 0 is 1. This is dE. Now this is simply 2 factorial, 0 factorial, 0 factorial. We call that 0 factorial is 1. Now 2 plus 0 plus 0 plus 2 factorial into 2a, whatever the area is. So we get 4a over 4 into 3 into 2, and we have a over 6. Now, it should be apparent that if Ni square, integral of Ni square is a over 6, then the integral of Nj square should also be the same, because in that case L2 will have power of 2 and L1 and L3 will have power of 0. So, but on the right hand side this doesn't make any difference, so we'll again get the same. So we can say that for this we have a over 6, and for this also we have a over 6 as the answer. Now let's take up this Nij integral, this one. So we have to evaluate Nij. We can write it like this: L1 power 1, L2 power 1, and L3 power 0. So alpha is 1, beta is 1, gamma is 0. So 1 factorial, 1 factorial, 0 factorial over 1 plus 1 plus 0 plus 2 into 2a, and then we get 2a over 4 into 3 into 2, which is a by 12. Now this is a by 12. This one is a over 12. And this one should also be a over 12. So the solution to this question is simply a over 6, a over 6, a over 12, a over 12. Or you can write it like a over 12 2, P1, not the same thing. This is how simple the factorial formula are. You can imagine the complexity of doing it, this sort of thing in 2D by longhand. Not that it cannot be done, but the complexity is immense. Now, there is another utility of natural coordinates apart from making integration very simple, and that is natural coordinates can be used to describe the geometry of the element as well. It is of little value in 1D elements, but for 2D and 3D elements, and particularly for higher order elements, which we have not studied yet, if the natural coordinates of a point P are known, for example, point P, natural coordinates L1, L2, and L3 are known, then it is possible and very easy to calculate the global coordinates of P, which will be X and Y. And that is done by using factorial, which in form is identical to the interpolation function for displacements. L1 xi plus L2 xk plus L3 xk. Similarly, y coordinate L1 yi plus L2 yj plus L3 yk. Let's do a problem demonstrating this process. We need to calculate the global coordinates of a point in element 3. This is element number 3. We know that L1 plus L2 plus L3 is equal to 1, which means that L3 must be equal to 1 minus L1 minus L2, which is 1 over 3. So L1, L2, L3 are 1 over 3. In other words, we are talking about the centroid of this element. The centroid will be somewhere around here, around here. But we don't know the exact location of the centroid. That's what we need to find out. X coordinate for this point, which is a global coordinate, taking node 2 as the I node. This is node I, and this becomes node J, and this becomes node K. So it means L1 x2 plus L2 x5 plus L3 x6. Similarly, y coordinate L1 y2 plus L2 y5 plus L3 y6. Putting in the values, all the L1, L2, and L3 all are 1 over 3, so we can take it common. Now, x2 is 3, x5 is 2, and x6 is 4. So this gives us 3 millimeters, which is very obvious. This is 3, it has to be. For y, we have 1 over 3, y2 is 3, and y5 and y6 are 1 each, and this gives us 1.67 millimeters. Now this is, as we expected, should be below 2, but we didn't know exactly how much. So this is the answer, is 1.67. So this centroid location in the global coordinates is 1.67. In the local coordinates, obviously, it was 1 by 3, 1 by 3, 1 by 3. Now note that all elements 1, 2, 3, 4, 5, 6 all have this centroid at 1 by 3, 1 by 3, 1 by 3. But when we come to the global coordinates, each will have unique different coordinates. When it comes to 3D coordinates, recalling that we have this sort of tetrahedron, and if we take a point inside P, then it will divide this into 4 volumes now, and the shape functions in this case will be L1 will be V1 over V, with V1 being volume opposite I node, L2 V2 will be L3 V3 over V, and L4 V4 over V. And we'll have all those properties. Adding L1, L2, L3, L4 will get 1, and the values will range from 0 to 1. And as far as the integration formula is concerned, the volume integral will take this form: L1 alpha, L2 beta, L3 gamma, L4 delta, volume dV, alpha factorial, beta factorial, gamma factorial, delta factorial over alpha plus beta plus gamma plus delta plus 3 factorial into 6. Now note that for line integral we have this L here, for area integral we have 2a here, and for volume integral we have 6v here. You'll recall that in our B matrix also we have in the denominator we have the same 3 quantities, and also in the expression for the shape functions we again have the same 3 quantities in the denominator for 1D, 2D, and 3D element. Thank you.